Sorry.
Nice. Hello and welcome back to Calculus 2, section 6.4 on shell method. So, it was an odd. I just hope that 6.4 starts with that sneeze. I want it so badly.
Shell method is nothing to sneeze at.
Yeah. Well, he's probably allergic to calculus too, so we'll see right by the end of the course. So shell method, guys. We are going to cut differently now. We're going to cut cylindrical shells. The first cuts happened perpendicular to the axis of rotation. We see where the object is round, and you stick the axis of rotation in the middle of that object, and when you cut discs, those discs are cut perpendicular to the axis of rotation. So if you have X, you will cut and make delta X slices, and if your rotation is Y, you will make delta Y slices. The cuts are always, for disc method, cuts are always perpendicular to the axis of rotation. Shell method is going to make cuts parallel to the axis of rotation, which means now your axis of rotation and your dx or dy will be opposite. Rotation on x will have dy, rotation on y will have dx. So now they mix. And that's very important because you don't want another method that does the same thing as the previous one, right? Now you want to have a mixed method, and this is the shell method. Now the shell method, what the shell method does, since it cuts parallel to the axis of rotation, it's going to create cylindrical shells. What is the cylindrical shell? It is literally just like, think of an eggshell, very, very thin, infinitely thin, cylindrical shell, and then like those babushkas, right? You put one inside the other, inside the other, inside the other, and then you fill out the entire space. Okay? So that's what we have for cylindrical shells. So if I have an object, we can just put a triangle, which will turn into a cone. So if I put a triangle here, and I rotate around y-axis, it will create the cone. So cone is created. Now, the way the slicing works is parallel to axis of rotation, which means you are cutting it with dx. So now, the y rotation formula will trigger volume equals 2 pi integral a to b p of x h of x dx. This is different than what you have in a textbook, guys. Textbook has a simpler version of this. This is more powerful, so I'll explain this. The one in the book is clear. So what do I have over here? Well, I have a perimeter, right? 2 pi r. And 2 pi r is the perimeter, and then you want to have times the height and times the width. So P stands for position, and H stands for height. Again, this is not in the textbook. This is a different, more I think, clearer and easier way to go about this. So I'm going to move rotation on top so that I can mark on this picture. Actually, you know what? I'll draw a new picture. So this is my rotation on y-axis, and I have my A and the B, and I have my representative rectangle dx. So now we see that the location for location for x, so this distance here is p of x, which is equal to x. So p of x is measured by x. And the height, h of x, is measured by f of x minus g of x. In this case, g of x equals 0 because it's just the x-axis on the bottom. So it allows for a whole bunch of different shapes, and it's really powerful. So technically, this works out to be the formula that you guys have in the book, 2 pi integral a to b x times f of x dx. This is the formula that is given in the book, but guys, this formula is a special case. It only works when you have this particular situation. What happens if you have an object that has a function on top, function on the bottom? It doesn't encounter for f minus g. And also, this x, you can move your axis of rotation not to be y-axis. Maybe you want to rotate around x equals 1. Then that x changes into 1 minus x. So there is a lot of conditions that have to be fulfilled in order for the formula that is given in the book to work. The formula that I gave you up there is leaves for much more customization and stuff. So let's take a look. Remember our 5-2 cone? Let's get 20 pi over 3 using the shell method, because we have to. It's the same dimensions of the cone, same object must produce the same volume. Yeah, we're using different method, but such is life. So we are rotating 1, 2, 3, 4, 5 tall, 1, 2. We are rotating this around y-axis. And the goal is to get 20 pi over 3, which is what we calculated already in 2 different ways, right? We use the formula, then we use the disk method, and now we want to do the shell method. So what do I have? Well, rotation on y means we have to use dx, so I'll draw the dx representative rectangle here. Volume is going to be equal to 2 pi integral, and I said your position is x. Your x limits are 0 to 2. And now your f of x, which is the height of this representative rectangle, which is stuck between the function and 0 on the bottom, so we don't have to subtract anything. Now f of x is equal to, your slope is negative 5 over 2 because it's 5 units up, 2 units over. 5 units up, 2 units, so negative 5 over 2, and then plus 5 because that is your y-intercept, right? You have to have plus 5. So now that is going to be multiplied by negative 5 over 2x plus 5 dx. So now just work your magic. What you can do is you can multiply this 2 inside to kill the fraction. That's a cool move. So pi 0 to 2, and now you have negative 5x squared, 2 and 2 canceled, and now you have plus 10x, guys, because the 2 distributes to both terms, right? I distributed 2 here and there. So 2 times 5 is 10, and then times this x here is 10x. dx, remember we are looking for 20 pi over 3. So this is pi we have negative 5x cubed over 3 plus 10x squared over 2 calculated from 0 to 2. So now pi, open parenthesis, again, these are all polynomials, you don't have to worry about 0. When you plug in 2, you get negative 5 times 8 over 3 plus 10, well, 10 and 2 cancel, so you just get 5 times 4. 5 times 4 and minus big fat 0 right there. So this is going to be pi. This is negative 40 over 3 plus 20. Common denominator here is a 3. And then you have negative 40 plus 60. And there's your 20 pi over 3. So we did this calculation now using the shell method. We are introducing the new method. Do we really need it? And the answer is yes. Some problems you can do with both methods. Just this one, right? Other problems can only be done with one method only. And some problems will be more convenient, so they can, both methods would work, but one method will be more convenient than the other. And the way you would know this is if you know how to play the game of these rectangles that are representative rectangles. I really tried to make sure you guys understand that for a single integral, you swiping from left to right with the representative rectangle or bottom to top, a representative rectangle has to ride same functions all the time. So when we had area between two curves, I said you can put dx rectangle here because top always rides f, bottom always rides g between the 2 points of interest, right? If you try to use dy, which goes like this, you see that both ends of dy touch the same function g, which is no bueno. Because in that case you have g minus g. You're not calculating anything. We also have seen the problem where your fast sine function was working with a slow sine function. And this was the place where, right, your f and g, and then g and f. So when they swap what's on top, what's on the bottom, they you have a new integral. So all of this stuff, when you're playing the game of these representative rectangles which move from left to right, all of that is still within the shell and a disk method, and that is the main player in deciding which method to use. Let's take a look at the shape like this. Let's say you go out 4 units and then 2 units. All right, there we go. Now these are linear lines, and you can quickly figure out equation for all of them. That should not be an issue. This is 1, 2, 3, 4, 5. 1, 2, 3, 4. So 4, 3. So you can quickly come up with your equations. This equation over here is y equals, it's a decreasing line, so it's a negative slope. The slope is 2 over 4, so that's 1/2, so negative 1/2 x plus 5, because 5 is the y-intercept. The one on the bottom has the positive slope of 1/2 x. You go 2 up and you go 4 over. 2 over 4 is 1/2. And you have your y-intercept to be at plus 1. See, now, having this, clearly the good choice is to use dx. See, dx is a good choice because you have top minus bottom there in terms of x. But then rotation is on y. And this is why you want the shell method, because the shell method will allow you to work with dx when you have rotation around y. That's what the shell does. The disk method, rotation around x, gives you dx. All right? So it might be confusing right now until you sit down to learn all the formulas and categorize everything. So you get to I'm just trying to find where's the page that summarizes this in a book. It's not as awesome as some other textbook that I like, but this one will hopefully do. Let me see if I can zoom out somehow. Can I zoom out? Yeah, I can. Good. And then make it. All right, so here is the, this is page something, something, something in the book. What's on the page are the 4 cases that you guys get to work with. And the important part is to realize that the dx integrals, your disk and washer method, dx and rotation on x, and your shell method, parallel, right, is dx, rotation is on y. Because dx is parallel to y. And over here, dx is perpendicular to y. So your representative rectangle has to be, for disk method, perpendicular, and for the shell, parallel. Same here for y direction, rotation on y, dy for disk and washer, rotation on x, and dy for the shell method. So these, so this page where they summarize everything, it's a good page to study. 446 in our current edition, but any calculus book you have is going to have the same page in. Great. So let's now talk about the shell method for the example that I have with this triangle. So I'm going to rotate this around y-axis and create this round object that has a spike on the bottom and spike on the top. Maybe you can spin it and balance it, and it's something, whatever it is. We don't care. The important thing is that it's round, right? It's like a flying saucer, right? Like UFO. That's what it is, right? With a very sharp edge at the end, right where the spike is. That's a very sharp edge that goes around. And you have a pointy top and the pointy bottom. So now we use shell to deal with this, right? We use shell. So volume is going to be given as a 2 pi integral 1 to, sorry, I lied. Integral, we're using dx, right? Because rotation is on y. Rotation on y implies dx for shell, right? So if it's a dx integral, then I need x limits, which are 0 to 4, because that's how far out delta x is going to go. It's going to start on the y-axis, which is 0, and then x equals 0, and then move out to x equals 4, taking on every value along the way. So the limits are 0 to 4. The position is x, and the height is the top minus the bottom. So negative 1/2 x plus 5 minus 1/2 x plus 1 and dx. Now I do have to calculate everything because I want to also force the disk method on this so we can see that this can do it, but it's painful. So 2 pi integral 0 to 4, and now it's time for us to add these. So minus half x is negative x times x is negative x squared. And then I'm not multiplying over here, I'm not foiling, there is a minus sign. I'm just adding and subtracting like terms. Keep that in mind. It's not a FOIL. So a half minus a half is minus 1. So minus 1x, which is minus x times x in front is minus x squared. 5 minus 1 is 4, so plus 4x, because you are still distributing this one. And then you have dx. So now we integrate this, 2 pi, and now when I integrate, I have negative x cubed over 3 plus 2x squared from 0 to 4. Two pi negative 64 over 3 plus 32 minus big fat 0, no one cares. We put this 32 over 1, then times 3 becomes 96. So 2 pi, and we have negative 64 plus 96 over 3. 96 minus 64 is very good. So 64 pi over 3. I'm sorry?
64 pi over 3. Oh, times 2. Never mind.
Times 2 in front, yes,
Yep.
in 2 pi. So 32 times, 32 times 2 is 65. I mean, stuff is working out today. I'm not making mistakes. I'm not sure why. I'm terrible with numbers. Good thing my livelihood doesn't depend on it. Yes? I'm sorry? No, when you look at it from the top, you have to see a circle, right? Because it's going to rotate around. All right, so now, guys, I want to do the same problem, but I want to use the disk method and see what kind of a pain would that introduce. I can't change the shape of graphs. I'm not allowed to change rotation. So that's going to bring up problems. So same problem done with the disk method. Same problem, disk method, and now we are going to understand, hopefully, why we need the other one. So now I am going to have the same deal. 1, 2, 3, 4, there we go. 1, 2, 3. Yeah, 1, 5, and then 3 out, so 4 out. 1, 2, 3, 4. And then draw this. Rotation is on Y. There's your X. There's your Y. There's your 1. There's your 5. There's your 3. And finally, your 4, 3. We are forcing disk on this. Again, there will be problems where you flat out you can't use a method at all. That's the next problem. This problem is both methods work. One is terrible, the other one is straightforward. So now I want the disk method. If I want the disk and I have rotation on Y, that means I must use dy. If I draw dy representative rectangle, what you immediately see is that the right-hand side of the representative rectangle doesn't ride the same function all the time. So how do we battle that when the function on one of the ends changes on you? Or both? How do you battle that? It was the first problem of today, right? You have to do two separate integrals. You have to do the disk method for the upper part separately from the disk method for the bottom part, and then add them together. And the reason for it is you have to use right minus left, but your right changes depending on where the x is. See that? That one is writing the function on the bottom, and then writing the function on the top is two different functions. Now we know that the bottom function was y equals 1/2 x plus 1, and the top function was y equals negative 1/2 x plus 5. Now both of these are useless to us in terms of x because our integral must be in terms of y, so we have to flip these and make them x equals everything else. So the y equals negative 1/2 x plus 5 will be changed into, you subtract 5 and multiply negative 2 everywhere. So x equals, right, you will have y minus 5 and then times negative half. So y minus 5, that's going to be, sorry, and times 2. So that's negative 2y, and then negative 5 times negative is plus 10. Did I get this right? He was like, yeah, whatever, just write faster. So we can be done, huh? We have 1/2 x plus 5, and then x equals negative 2y plus 10. So minus 5 times 2 positive 10, negative, yeah, plus 10. Good. The other function, y equals 1/2 x plus 1, turns into x equals, and now it's y minus 1 times 2, so 2x minus 2. 2y minus 2. You must switch the functions from x to y because your dy forces you to have integrals in terms of y. Now we are going to do the disk method for half of the problem, the bottom half, and then the upper half. So the volume created by, let's say, the bottom half, so volume bottom, is going to be pi, and now I need my limits for y, that's 1 to 3. And then we are going to take our 2y minus 2 squared, that's the function on the bottom, minus 0 squared, no one cares, dy. How's my battery doing? 30%. All right, let's try and see. So this should be simple. FOIL. We get 4y squared minus 8y plus 4. Don't forget the middle term, dy. Plug in. Well, now you integrate. So that's 4y cubed over 3 minus 4y squared, because it's y squared over 2, and then 2 and 8 cancel, plus 4y computed from 1 to 3. We have to compute everything, so that's pi. When you plug in 3, you get 27 divided by 6, 9 times 4, 36. Minus, another 36. Plus 12. Minus, we have to use 1 now. 1 cubed is 1, so that's 4/3. Minus and minus gives you plus 4. And then minus 4. So this is pi. The only thing that it survives is 12 minus 4/3. Now 3/3 is going to take away 1 from 12, so that's going to make it 11. You still have 1/3, so 10 and 2/3 is the answer. So pi times 10 and 2/3. Now that's 32 pi over 3. 32 pi over 3. What do you have over here? 64 pi over 3. Isn't this symmetric? The top half is the same as the bottom half? Yes, it is, right? So we already know we're good. But we're still going to calculate the other one, because not every problem is symmetric. So now, the volume for the upper part, VU, is going to be pi times, now we go 3 to 5, and we are using the upper equation, which is negative 2y plus 10. Oh, we're going to regret this very quickly. Squared dy. It's a pi integral 3 to 5, 4y squared minus 40y, 2 times 2 times 10. Right? It's 2ab in the middle. And then plus 100 dy. We have pi, and now we're going to integrate, which means, open parenthesis, 4/3 y cubed minus 20y squared plus 100 y computed from 3 to 5. This is equal to, you plug in 5 first, so you get 125. 125 times 4 is 500 over 3. Minus 25 times 20, it's 500. And then plus 500. Okay, that's convenient. Dead. Minus, we have 4/3 times 27. Plus 9 times 20, 180. Minus 300. This is awesome. Pi, we have 500 over 3. Minus 3 and 27 cancels down to 9, so that's a 36. And then minus 120, because 180 minus 300 is 120. 120 minus 36, that's going to be 84. So we have pi 500 over 3 minus 84 over 1. Multiply that by 3. So 500, I don't need the parentheses anymore. 84 times 3, that's 240, and 12 gives you 252. 252. Well, this is terribly wrong, right? Because we did not get what we need.
You did negative 120 plus 36, not minus. Because they're both minus. So it needs to be negative 120 minus 36.
Oh, that's negative 156. Well, thank you very much. That changes our calculation. When we multiply 156 by 3, guys, 100 times 3 is 300, 50 times 3 is 150, and 3 times 6 is 18. You add this to 468. Hey, that's 30. That's 32. Pi over 3. So the total volume is the volume for the upper plus the volume for the lower. Did I say bottom or VB? Okay, VB, fine. Which is 32 pi over 3 plus 32 pi over 3 gives us 64 pi over 3. Well, that took forever, and finally we have mistakes, right? So this is a problem where shell method was more convenient than the disk. Still, both are possible, but the disk, you had to use 2 integrals. Now, yes, you could have solved this problem just with the 1 integral and then doubling it, but most of the time it's not symmetric. So you have to do both integrals because you couldn't double it if it's not symmetric. So we saw an example, the first example I did for shell, where we obtained the same 20 pi over 3. This problem was easy for disk. This problem was easy for shell. Doesn't matter which one you use. The next problem with the flag, we did it with a shell. It was a joke, and then it took us forever to work out 2 integrals and add them together for the 2 volumes in this case. And now, as the last problem that we look at for the shell method is going to be a problem where it is impossible to use disk. You cannot use disk at all because it will have that feature where the function bends in a way where if you put dx or dy, you cannot set up the problem at all. So I just need to find an example so I'm not, making stuff up. Oh, perfect. The first example, number 9, is exactly what I'm talking about. So we have y equals negative x squared plus x on the interval 0 to 1. And they're asking what's the volume as you are rotating around y, right? This is a problem where disk doesn't work at all. Let's see why. You are going to draw there's always a way to force it, but I won't say at all. So you draw the function, which is this downward opening parabola that starts at 0, ends at 1, and your rotation is on y. If you want to force, don't write this, you want to force disk, well, it's disk and you have a rotation on y, you must use dy. Now what happens as you put dy? Left end and the right end are riding the same function. Well, you subtract it to 0 and the whole procedure goes to hell, right? There's nothing to compute. So it cannot be set up at all as a disk method. So disk cannot be used at all. Disk method cannot be used here, right? Meaning this problem. But what you know for the shell and the y rotation is that will give you dx because you memorize the formula. So here's my dx representative rectangle, and it's great. Bottom always rides the x-axis, top always rides the polynomial, therefore we are able to set it up. So volume is 2 pi integral 0 to 1, because it's a dx integral. Position is x. The function is good old negative x squared plus x, and then you have your dx. So now it's easy peasy, right? 2 pi integral 0 to 1 of negative x cubed plus x squared dx, and this is equal to 2 pi, open parenthesis, negative x to the 4 over 4 plus x cubed over 3, computed from 0 to 1, and we don't have to worry about 0. Well, we don't have to worry about 1 either, because it's just 1. So negative 1/4 plus 1/3. That turns out to be 1 over 12, which is pi over 6. And that's the volume, pi over 6. About 1/2 units cubed, because pi is about 3. So, before I shut off the stream, I just want to put this chart of choices. So if you have disk and x rotation, you will be using dx. If you have disk and y rotation, you will be using dy. If you have shell and x rotation, you will be using dy. If you have shell and the y rotation, you will be using dx. Now you will have to untangle all of these, right? Disk method, shell method, they have different formulas. They are applied differently. They cut differently. Over here, I'm just going to put in parentheses perpendicular cut, and over here in parentheses parallel cut. So we know that dy is horizontal and the x-axis is horizontal. They are parallel. Remember, the dy is the cut. And then you also have y-axis being vertical, dx being vertical. They're parallel. So that's the parallel cut. The question is, maybe, I'm not even giving you a chance to ask that question, how do I know which method to use if it's not specified? The answer to that question is experience. That's why you have homework. You are most likely not going to know which method to use when you just see a pile of equations. You can't know. You just saw this for the first time ever, right? No one knows when they see it for the first time ever, which is why there is homework to gain that experience so that you can make the choice. Now, clearly, for disk method, they only have disk problems. But when you jump into the shell section, you are going to see the mixture of problems. And some of the problems will ask you to choose. In some problems, like problem number 12, it is obvious what you have to use. So problem 12 has the two functions that intersect like this. And it has a rotation on the y-axis. So the shape of the functions in this case is forcing you to use dx, right? The shape of the functions is forcing you to use dx. So functions are forcing use of dx, and then you have dx plus rotation on y will tell you which method you use. You see that? So it's not you decide the method and then try to fix the formulas. In some cases, the way the problem is posed will tell you, well, you must use dx because dy will not work, period. Look, dead. It folds on the same function. So dy is useless. So you are forced to use dx, and because you are forced to use dx, and rotation is on y, you can't change that, dx plus y will give you shell. Dx rotation on y is shell. So any of the two pieces of information could be given to you, and then you will be deciding the third piece of the puzzle, and then you know. So you either know the method, you always know rotation. So you either know the method or the functions guarantee. Now, in those vanilla cases, like we had that cone, anything goes. Cheap problems that you can, right, plug anything anywhere, it's great. You can use whatever. Let's see if they have some spicy. Whew, they do have spicy. Problem 51. For those of you who want to be advanced in this stuff, take a look at a problem 51. You take a circle and you rotate the circle around the y-axis and you create a donut. That shape in mathematics is called torus. And that shape is very important because, first off, the new transformers that we use, not talking about Autobots, I'm talking about electronic components that are in your chargers. They used to be huge bricks because the transformers inside that reduce 118 volts from the wall down into the 12 or 9 volts or whatever you need to charge your devices, they used to be like boxes, right? Squared and like cubes and so on. And it had a lot of waste of electricity because of eddy currents and some other stuff. And then someone figured out to make a donut-like ferro core and then wrap the transformer around the donut one. They were able to reduce the size from a brick to like nothing, having the same power, having no waste, do eddy currents and other things, right? So in the design, these things are important. If you want to be advanced, as I said, then go ahead and figure out how to work out the circle that rotates around, and then figure out the volume. Now, obviously, you can't rotate the circle. You can rotate the half of the circle and multiply, because the top part of the donut and the bottom part of the donut will be the same. So you can just do the upper half, which is going to be the square root of, let's say, 16 minus blah, 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 whatever your function is. Now, remember that circle is shifted, so the equation is going to address that, because it's going to be shifted on x-axis. So it's x minus whatever equal the radius and so on. And once you figure that out, then you can work better in the realm of physics and electrical engineering and whatever the donut shape for is used. And also as a plus, this is just a side. Anytime your friend is having a donut, you can, bring this up and annoy them until they leave, so you can play games in peace. All right? I will see you tomorrow. We will continue 6.5 and 6.6, which are on length of curves and surface area. We might even push 6.7 and finish the chapter depending on. Tomorrow I will also talk about labs. It's important for everyone to have lab partners. I did say the day one that labs with the only one name on them are not accepted because the rule of the labs is it's a group work. You have to collaborate. So the minimum of 2 people. My suggestion is 3 or 4 per group. Sometimes you guys go up to 5 and 6. I don't, whatever. But if the group is too large, you have issues to meet. If the group is too small, if someone leaves, you're doomed. So there's a lot of, right? 3 or 4 people per group, 5 even, right? That's a good size. 6 gets to be really obnoxious for you two guys to meet outside of the classroom and do work. So we'll discuss labs tomorrow, and your first exam will be after chapter 7. So first exam, we had that list yesterday. First exam is chapter 6 and 7. So we'll see when. See you tomorrow.